Okay, welcome to lesson 1.4, the limit of a function. In the last lesson, we used limits combined with the difference quotient, and we were focusing on calculating the instantaneous rate of change or the slope of the tangent at a given point. In today's lesson, we're going to use limits to investigate the value of a function. That means like the y values of the function as we approach a given x value. So this can be useful when we're investigating the behavior of a function near a possible discontinuity. Maybe there's a hole, maybe there's a vertical asymptote, or maybe there's a jump in the function. Also, we can use this idea to help us investigate the end behavior, which we're going to look at in chapter 4. Okay, so the notation today, just slightly different. Now, instead of the limit as h approaches 0, it's going to be as x approaches a certain value. And over here is just going to be the function itself, f at x. And I read this notation here as the limit of f at x as x approaches the a value is equal to L, and L will be the limiting value. So for example, we're going to look at just the function x squared, our basic parabola from grade 10. So the limit of x squared as x approaches 3 is 9. And that makes sense, right? That as I get closer to 3, the height or the y value of the function will get closer to 9. Now, when I get closer to 3 on the graph, which direction am I coming from? That's something that we need to think about. So when I ask if the limit exists, because sometimes it won't, for instance, if there's a vertical asymptote, the limit often does not exist. So the limit of f at x as x approaches a exists if and only if, and that means it goes both ways, the limiting value from the left equals the limiting value from the right. So I'm approaching the limiting value means the y value that I'm approaching from the left is the same as the y value that I'm approaching from the right. So in notation, what that looks like is if the limit here, this is the limit from the left, so I'm approaching a from the negative side of a, of f at x is equal to the limit of f at x as x approaches a from the right, or from the positive side of a. So we're just going to add that into your notes so we don't forget. This here is what we call the left-hand limit. And this here is the right-hand limit. Right, a little bit bigger than a, and this is a little bit less than a. So if the left-hand limit is the same as the right-hand limit, then the limit altogether or overall does exist for the function. And vice versa. If I know that the limit of the function exists as x approaches a, then that tells me that the left-hand limit must be equal to the right-hand limit at that point. So let's take a look at an example so hopefully we can make some sense of this notation. The first thing we're going to do is take a look at a radical function. And in order to come up with these limits, first we're going to look at a graph, just so we have that visual idea. So here I've got a radical function. I know that there's been a horizontal reflection. I know that there's been a shift 5 to the right and a shift 1 up. So I'm going to draw a picture of this graph. It tells me that the starting point, remember that the regular root graph has a starting point at the origin. That starting point has been shifted 5 to the right and 1 up. And then from there, it's going to open to the left instead because of the horizontal reflection. So I know that I need to be able to see over to 5. And again, when you label your x-axis, make sure you label enough so that I don't have to count out. Right? If you just label the ones around here, then I have to count squares and make sure you're in the right spot. That's not strong communication. And then you can label your y-axis. You don't have to label every single square, just enough so that people aren't having to count their way up. Don't forget to label the x and y axes, and there should be arrows on the end of the axes to show that that does go on forever into infinity. All right, so like we said, this graph starts over at x is 5, y is 1. And then from there, it just has the basic pattern of a radical function. So if I go up 1, I should be going over 1. And then from the vertex, or the starting point of this graph, if I go up 2, I should be going over 4. There's my next point. Or if I go up 3, I should be going over 9. Right? Because I'm thinking about square rooting these numbers. And then I can just connect this into a smooth curve. I find this really hard to do on the tablet. Yay, okay. So there we've got our function drawn, and now we're going to take a look at some of these limits and what does this mean. So the limit of the function, so we're looking at what's the y value approaching as the x value approaches 1. So on the graph, as I get closer to x is 1, and I mean from either side, so as I get closer from the right and as I get closer from the left, what is my y value approaching? And they're approaching the same from the left and the right. So that tells me that the limit of f at x as x approaches 1 is equal to 3. And so I'm just going to write off to the side here what I was thinking so that you've got that. So as you get closer to x equals 1, from the left, this is important because it's got to be both. And so notice that I don't actually care what happens when I get to x equals 1. I only care about what's happening as I get closer to x equals 1. And we'll take a look at what that means more when there's a hole, for instance, on the graph. So next I'm going to take a look at the limit of f at x as x approaches 5 from the negative side. So this is the left-hand limit. And so I'm getting closer to x is 5. I'm sliding along the curve, and I'm sliding in from the left towards 5. And what I notice is that the height of the graph, the y values of the graph, are getting closer to 1. So this is equal to 1 here. Now the next question here is asking about what happens as I slide in as x approaches 5 from the positive side, or the right side. And what you notice here is from the right of x equals 5, the function just doesn't even exist. Right? Like if I went over here to like 5.1 or 5.2, the function doesn't exist for me to slide in closer. And so this function, or this, sorry, limit also does not exist. Just going back to this one up here, what I was thinking was from the left of x equals 5. Y gets closer to 1. All right, the last one we've got here then is what is the limit of f at x, the limit of the function, as x approaches 5? So now I'm talking about the definition. Remember that the definition says that the limit as x approaches a of f at x will exist if the left-hand limit is equal to the right-hand limit. So when I look at the left-hand limit and the right-hand limit as I approach 5, they are not the same. So this does not exist. And that's because the left-hand limit does not equal the right-hand limit. All right, let's take a look at another example. In this one here, we're taking a look at a piecewise function. Remember, a piecewise function is when I have several different equations for the same function, and each equation is defined on a different part of the domain of the function. So when I look at this function, it says that I'm going to use this parabola as long as x is less than 4. And then I'm just going to skip over this middle part. If x is bigger than 4, I'm going to use this radical function, this root function. And then at the point where x is equal to 4, I'm just going to say that the value is negative 4. So we're going to sketch a graph of this so that we kind of know what it looks like, and then we're going to actually figure out, well, what is the limiting value as I approach x is 4? All right, so for this one here, you're going to find that you want to see y values from -4 up to +6 for my y values. And then for my x values, make sure that you can see over to 8. Again, don't forget to label your x and y axes, and there should be arrows on the end of the axes. They were provided for you here. All right, so first we're looking at this parabola. Now this parabola has been shifted over to a vertex of 4, 2. If you don't remember how to graph parabolas, you can go back online and find a video for that. So over to 4 and up to 2, and that's where the parabolas are going to start. Now I don't know what's actually happening at 4, so I'm just going slightly to the left of that, and then from there the parabola is going to go over 1, up 1, like a regular parabola, and then over 1, up 3, and that's what my parabola is going to look like. It's getting really close to that vertex, but I'm not actually sure if it runs into it or if it's an open circle, like a hole there. What I do know is that when x is actually equal to 4, the y value is -4. And that's a closed circle because that's actually happening. That tells me then that the parabola can't have a closed circle here, or it wouldn't be a function. It is an open circle here. Now we're going to take a look at the last part, or the right part of the function. It's a root function that also starts, you can kind of think of this as like the vertex, right? Same sort of idea here. It's moved over to 4, 2, and then it's just a regular root function. So if I go over 1, I go over 1, up 1, or if I went over 4, I would go up 2, and that's what my root function will look like. And again, an open circle at the starting point of that root function, because its x is greater than 4, but we're not actually going to equal 4. We're getting really, really close, but not getting there. So a hole there, and we call this a jump discontinuity. So there's a hole, but we call this a removable discontinuity, where I've like removed a piece of the function and it's appears somewhere else. Okay, so we're going to look at the limit of f at x as x approaches 4. Well, to do that, I'm going to look at the limit as x approaches 4 from the left side, so the 4 negative. It's like a little superscript on the 4. So I'm looking at coming in from the left of x equals 4 and sliding in towards x equals 4, and I'm asking myself, what is the y value getting closer to? And I can see that it's getting closer to 2. So this was my left-hand limit. Next, I'm going to show my work by looking at the right-hand limit. So I'm looking at the limit of f at x as x approaches 4 from the positive side, or from the right-hand side. So now I'm coming in from the right-hand side of 4 and I'm sliding in towards, and I can see again that my y value is getting closer to 2. So this is the right-hand side. Now by the definition, if the left-hand limit is equal to the right-hand limit, then the limit exists and it equals that same value. So what we have then is that therefore the limit as x approaches 4 from either side of f at x is equal to 2. So what's special about this question, what we want to notice here, is that the limit is 2, even though if I were to calculate f at 4 exactly, it is not equal to 2. F at 4 is actually equal to -4, not +2. So this is important, that I can have a limit even though the point doesn't exist there. All right, in our next example, we're just looking at some algebra, and we're going to evaluate some of these limits. If the limit doesn't exist, we're going to have to explain why we know that. Okay, so first thing we're doing is taking the limit of the line x minus 3 as x approaches 2 from the right. Now notice that these brackets are here and they are important. It does make a difference. If I didn't have the brackets, then I would just be taking the limit of x as x approaches 2, and then I'd be subtracting 3 from that answer. So it will make a difference in some questions. All right, so because this is a line here, I know that I can take the limit as I approach 2 from the left. I know that the domain here of this function is x belongs to the set of real numbers. And so we're going to be looking at this in our next lesson too, different properties and how I know when I can just plug the number in. So here I know that I can just plug the number 2 in. It all kind of comes together once we get through all of the lessons in this chapter. So I've plugged in 2 for my x value, I've taken the limit, and I get -1. If I think about what this graph looks like, right, there's the y-intercept at -3, and then it's just got a positive slope, and I'm asking what's happening when the x value gets to 2, and we're saying, well, it's at -1, right? That's what we're sliding in from the, from the right. So we're sliding in towards that point from the right, and we're saying, well, yeah, the height of that point is getting closer to -1. All right, for our next function here, we're looking at the limit of this rational function as x approaches 1, again from the right-hand side, the positive side. So again, if I plug 1 into this equation, I'm not going to be breaking any algebraic rules, and we're going to look specifically at when can I do that tomorrow. So I can take the limit here, and I can just plug 1 in. And now I can calculate this out. So in the denominator, I've got 1 minus 9. That's -8. And then when I reduce this to lowest terms, I get +1/4. And again, if you wanted to think about, well, what does this function look like? There's a vertical asymptote at -3 and +3. If I factor that denominator there, I'll get 2. And this is one of those rationals with the kind of flattened parabola in the middle. And then the 2 sections on either side. Okay, and so we're looking at what's going on at 1, and we're saying that that point there is getting closer and closer to a height of 1/4. Remember here, we're not talking about the slope of a tangent today, right? We're just talking about the y values, what's happening to the y values as the x values approach a certain point. All right, our next one we're looking at a rational function. This one's a little bit different. Remember in our last one we were looking at the point 1, but my vertical asymptotes were at -3 and +3. This one's a little bit different because we know if I plug 5 into this denominator, I'm going to get 1 divided by 0, which is not allowed. So I can't sub in here. And hopefully you remember from advanced functions that this is going to turn into a vertical asymptote. So what I have to do to show what's going on here is I have to investigate the limit on either side of the point. So I'm going to do the left-hand limit of the expression. And when I do this, I'm thinking about plugging in a value that's a tiny bit smaller than 5, right? I'm on the left-hand side of 5. So for some people, it helps at the beginning when you're just starting to work with limits to actually pick a number that's a tiny, tiny bit smaller than 5. So like I want you to imagine like 4.9999, like keep going with those 9s, like really, really close to 5, or just a tiny bit smaller. So if you imagine what would happen then, when I do 4.9999999 minus 5, is I would get something really close to 0, but it would be negative, right? It would be negative 0.000000 and eventually a 1. So in order to write that in a quick notation in math, we say it's really close to 0, but on the negative side of 0. So it's similar to this notation here in my limit. And then the numerator is still just 1. So I took the limit here, and what I got was a number that's really close to 0 but negative. And now I want to imagine taking that 1 and dividing it into parts that are 0.00000001 big. Well, if I do that, then I'm going to get a whole bunch of parts, right? If I take $1 and I divide it into tiny, tiny fractions of a dollar, I'm going to get a whole whack of these little groups or little piles. And so this is how I get an infinity, right? The more 9s I put here, the smaller the groups and the more pieces I will get. Except that I've got a positive divided by a negative, so I'm going to be getting closer to negative infinity. So we're going to use this idea of like 1 divided by close to 0 is an infinite amount. Now we're going to take a look at the right-hand limit. So the limit as x approaches 5 from the positive side. again, of our function. And this time I'm imagining that x is something just a little bit bigger than 5. So again, as you're getting started here, it sometimes helps to like actually pick a number, but you'd be like putting a whole bunch of zeros and then a 1 somewhere at the end. Then what you want to think about is, well, so again, we can punch that in. What we would get then if we did this number subtract 5, we would get 0.00000. So it's like super close to 0, but positive. So just a tiny bit bigger than 0. And then if I think about dividing this, so I've got 1 divided by that 0.000001, again, I would get a really big number. And this time I'm doing a positive divided by a positive, so this would be a positive infinity. So what I've got here is that the left-hand limit is getting closer to negative infinity. This is not actually a limiting value, so technically we would say that this limit does not exist, but we can write this notation that the limit as x approaches 5 from the negative side is negative infinity. But from the right-hand side, it's approaching positive infinity. So therefore, these limits are not equal, and we say that the limit of the function as x approaches 5 does not exist. And just for a quick visual, hopefully you remember what this function looks like, but there's a vertical asymptote at 5 for this function. This is our grade 11 function, right? The reciprocal function's just been shifted horizontally 5 units. So that kind of makes sense, right? That from the left, I'm approaching negative infinity. From the right, I'm approaching positive infinity with my y values. And so, of course, there is no limiting value. These are not running into each other as I get closer and closer to 5. All right, next we're going to take a look at this function here. Again, if I imagine plugging 2 into this, I would get in the denominator 2 squared minus 4. That's equal to 0. So I can't actually do that. So kind of like yesterday, we're going to see if we can play around with this guy and simplify this expression. So the denominator, I notice, is a difference of squares. So I can write x plus 2, x minus 2, or you can write the brackets in opposite order if you did x minus 2 and then x plus 2. That's fine as well. And now what I notice is that I have a matching bracket in the numerator, or a matching factor, that I can cancel. So now I'm left with 1 over x plus 2. And at this point, I can take the limit. I can plug in x equals 2 to this equation, and I get 1 over 2 plus 2, which is 1/4. Now, we know that if I were to graph this function, the function does not exist when x equals 2. What happens here when I have a canceling factor, hopefully you remember this from advanced functions, that's a hole on my graph at x equals 2, but there would be a vertical asymptote at x equals negative 2. So if I were to look at this one, again, I'd have a vertical asymptote at negative 2, but then when I got to 2, I would have a hole. So it would come along here, and I would have a hole here, like this. So the height of the function is approaching 1/4, but it does skip right over, and that's okay. When I get to a hole, there is still a limit. It does still exist. All right, on the last page of today's lesson, there's 4 true or false questions, and it's just getting you to think through some of the notation here. So the first one here, the limit of the function as x approaches a may exist even if f at that a value does not equal the limit of f at x as x approaches a, and even if f at a does not exist at all. Now, I'm not going to answer these true or false questions in today's lessons. I actually want you to go through this notation and try to understand it, because it's all foreign to you right now. So I want you to think about it, add some numbers in for the A's and the L's, see if you can draw a connection between these and some of the examples that we already did in this lesson. And I will take them up in the next lesson. Enjoy your homework. It's on the homework log.